Hello, welcome to my presentation, and thank you for the organizer for inviting me. So today I will talk about two words, soft robot manipulation through model-based sensing and control. So of course, the motivations, so basically the motivations are, in a normal world, I think even soft robots should be able to serve a coffee. So the goal of our work was to be able to manipulate a cup of coffee with a soft trunk. And basically we came with this proposition of using inverse kinematic with non-slipping contact. Basically, let me present the output of this work. The output is like having this cup, and you see that you can control directly the motion of the cup inside the trunk. And basically, when you want to move this cup of coffee, you find out how to change the length of the cable inside the trunk to manipulate the cup. So we will talk about mechanical model for the soft trunk, the inverse kinematic for the deformable robot, inverse kinematic with contact. And then we will see other applications for manipulation of deformable objects and sensing in soft structure and proprioception. So let me talk first about how we create this model. So this soft trunk is composed of deformable robot made of with 8 cables. So you have 4 cables for section 1, 4 cables for section 2, going through all the object of the robot. So you can create a FEM model. And out of this FEM model, you have the internal force, and we add some constraints for the modeling the cable. So basically, we use a time-stepping method for dealing with contact. We use one linearization per step for the internal force, and basically you obtain a matrix system here at each time step, AX equal to B. So B is something you can compute directly from the initial vector at the beginning of the time step. And here you obtain a new variation of velocity, which is your unknown at the end of the time step. So if you want, you can obtain the same kind of equation with a quasi-static case. You obtain A, also X equal to B. So the first question to ask is what space we will use. We have different space in particularly in soft robotics. And with using a numerical model, you have the size of the mesh, which gives us the number of degrees of freedom. It's linked to convergence. So it's there is also another space, which is the ghost point that we are using in FEM, which is used for the constitutive law. The number of degrees of actuations are much smaller than the degrees of freedom, so we are in under actuation case. And the degrees of sensing are also much smaller than the degrees of freedom. We are under observations. So we also have other space for interaction like contact, friction, etc. So that to basically to go from space to another, we are using Lagrangian Mechanics. So again, we have this, remember that we have 2 types of equation, dynamics and quasi-static. You can basically play with the space. So you have 2 types of projection you can do. One is Doph reduction or composition, which is projecting this matrix in a subspace. Okay, to have a reduced space. And another way of using Lagrangian mechanics is to select some Doph, and then you use Lagrangian compliance projection. So here you work in the inverse with the inverse matrix here. So if A is homogeneous to a stiffness, A minus 1 is homogeneous to a compliance. And you can project, you can select some particular Doph, for instance, for actuation, or particularly when you are looking for a small number of Doph compared to the size of the model, to really drive the model in this space. So for the inverse kinematic, we will use this compliance projection. So basically, again, you have this matrix system. You have the force created by cables. You can either impose a force by imposing the force to apply on lambda. HT is basically when you move the cable, you apply some force on different node of the mesh. Okay, so when you impose the force, it's really easy. It's basically you impose this force, but when you impose the length, it's already a little bit more complex because you impose the length, but you have to have you can only pull on the cable, you cannot push, and you can only pull when the cable is tightened. So you have to verify that the cable is tightened. So this value is equal to 0. And then in that case, lambda could be equal to something non-zero. If you look at the kinematic model of a soft robot, we will use this compliance projection to compute that. So this compliance projection allows us to write basically the length of the cable with directly connected with the force of the cables. That's what we have here in this equation. Here, delta here is the measurement of the length as we had here. So it's measurement of the length based on, so the variation of the length based on the variation of the force on the cable. And here you have a projected compliance. And you can add a new constraint for the effector, for the end effector position. And so the variation of the motion of the end effector position is related also to the force in the cables. And basically you can inverse this equation, so inverse WAA, because it's a square matrix. And when you do that, you have the variation of the position of the end effector based on the variation of position of the actuators. So here it's directly a Jacobian. It's exactly like a Jacobian of a rigid robot, except that you take into account the compliance of your robot. When you want to inverse this model, as we do also with rigid robot, you can use quadratic programming algorithm, again with using the compliance matrix. In that case, you minimize the distance between the end effector position, the current end effector position, and the desired position of your end effector position. And you can impose, using the constraints in your PP, the fact that you can only pull on a cable, and the fact that, for instance, you have a course, minimal and maximum course of the actuators. As you have more cable, so the number of degrees of freedom of your cables, which are 8 here, are greater than the end effector position, which are 3 here. You have a multiple solution. So you can, when you have a position, you have multiple ways of actuating the robot to obtain the desired position. So to obtain a unique solution, you can add an expression of actuator mechanical work. Basically, it's written like that. It's also based on the compliance projected in the actuator space. Then you can add a part of this, a small part of this actuator work in your minimization program. In practice, it allows to obtain a unique solution. So it's what you can observe here. You can directly pilot the end effector of the robot. The problem is that here we want the robot to go into contact with an object. And so you have first to solve the problem of contact, of collision. And in collision, when you have collision, you have basically linear complementarity constraints in your minimization problem. So it means that basically a contact can be active or not. if it's active, it's so basically the lambda is positive and the contact is so the contact distance is 0, or this contact distance is positive and lambda is 0. And that's what we will find in the solver that we have built for this solving this QPCC problem, so quadratic programming with complementarity constraints. So basically, imagine that we start from this position where we have one active contact. We will solve the first QP with this contact which is active. We will reach a boundary. So imagine that you want to go in this direction. You will have this contact that will be a candidate for pivot. So this contact was inactive and it becomes active. You have a new set of active contacts. This equation. Then you will solve a new QP with 2 active contacts. And then if there is no other candidate for pivot, you have your solution. And that's what we have here. So imagine you have this robot, this trunk robot that you want to move from this point to the other point. Okay, and you have an obstacle that is not model. Obviously, if you don't take into account the obstacle in your inverse plan, as you see here, you have a discrepancy between the model and the reality. And the robot is not able to go to the targeted position due to the obstacle. But here on this robot, we have also added one actuator, which is the movement of the base. And you will see that here we model basically the obstacle in the inverse problem. We have the contact that appears and disappears here. And you see that the inverse model is automatically able to adapt to reach the position of the inverse problem. We have extended this work for frictional contact. So it means and not friction, so frictional, I mean sticky contact, so contact that actually there is no dynamic friction, there is only static friction. And it allows to solve also the problem of locomotion. So here it's an example of this paper. It's not our invention, but you have a deformable wheel that can be deformed by changing the length of the cables inside the wheel. So, and in our inverse problem, the idea is to find the length of the cable, that how we change this length given the motion of the wanted motion of the center of gravity of the wheel. So as you see here, when we change the desired motion of the center of gravity, automatically we found how to change the distance, the cable length to place correctly the center of gravity. And as I showed you before at the beginning of this presentation, we are also able to deal with manipulation thanks to the modeling of stick contact between this cup and the deformable trunk. This allows also to control manipulation. So here is the inverse. We manipulate a deformable object, and the contacts are due to a rigid hand. As you see, we control basically the motion of a point inside several points on the deformable object. Okay, and you see that when we want basically to deform some point, the robot finds how to adapt the articulation space to obtain this deformation and the manipulation of the deformable object. It's still it's only simulation. Has not been demonstrated on the real world. What we would like to do in the future is to have also a force and state estimation, also based on inverse modeling. So we have done that recently, thanks also by an adaptation of our inverse model. Here we add a new constraint again. which measure, for instance, the volume, the change of volume inside the cavity. And thanks to this change of volume, we can estimate by the inverse the force applied on the robot. So we have done that on this small finger. You can see here that by measuring the airflow on the cavity that are placed on this finger, we are able to find the force applied on the finger. And you see that we can also have multiple forces. On the finger, we have capacitive sensors so to know the location of the force. And thanks to the airflow, we measure the intensity of the force of the user. And it's also compatible with actuation. So here we have a cable, you see, and the model is able to adapt to this change of actuation state. Thank you very much for your attention. And I will be happy to answer your questions. Maybe you can on chat or you can send me an email. Don't hesitate.